Hey everyone, and welcome. Today we are diving deep into one of the most incredible partnerships in all of physics, the invisible link between electricity and magnetism. It's the force that powers pretty much everything around us, so let's get into it. So let me ask you this. What could a massive bolt of lightning possibly have in common with a little magnet that holds up your shopping list? I know, it sounds like a weird question, right? One is this huge, chaotic burst of energy, and the other is just sitting there. But believe it or not, they are born from the exact same physical principle. And by the end of this, you're going to see exactly how. Okay, so our story has to start at the very beginning with a simple question. Where does magnetism actually come from? And I'm not talking about your everyday permanent magnets just yet. Nope, we're going right to the source of the whole phenomenon. And here it is. This is the single most important idea we're going to talk about. Anytime an electric charge moves, I mean any charge, whether it's a single electron flying through space or a whole river of them flowing through a wire, what we call a current, it generates a magnetic field. That's it. That's the ultimate source. Moving charges create magnetism. So how do physicists actually calculate this stuff? Well, they use a fundamental rule called the Biot-Savart law. Now, don't worry, we're not going to get lost in the weeds with the math here. Just think of it like a master recipe. It tells you exactly how to calculate the strength and direction of the magnetic field from any tiny little piece of wire that has a current running through it. So let's take that master recipe and apply it to something simple, like a long, straight wire. The law spits out this neat little formula. Again, don't worry about the symbols. The point is, we have a precise way to describe the magnetic field. But what does this invisible field actually look like? It looks like this, and this visual is just perfect. You can see the magnetic field isn't pointing away from the wire. Instead, it wraps around it in these perfect concentric circles. And it's pretty intuitive, right? The stronger the current, the stronger the field, and the farther away you get from the wire, the weaker that field becomes. Okay, so what if we take that same wire and bend it into a circle, into a loop? Well, look what happens. All those little magnetic fields from each tiny segment of the wire, they all add up and get super concentrated right in the center. This creates a way stronger field, and it's basically the secret sauce behind how we build powerful electromagnets. All right, so we know these fields go in circles, but which way? Clockwise? Counterclockwise? How do we know? For that, we've got one of the absolute handiest tricks in all of physics. It's called the right-hand rule, and it works in two slightly different ways depending on the shape. So for the straight wire you see on the left, you just point the thumb of your right hand in the direction the current is flowing. The way your fingers naturally curl, that's the direction of the magnetic field. Easy. Now, for the loop on the right, we kind of flip it. You curl your fingers in the same direction as the current flowing around the loop. And now your thumb points right in the direction of the magnetic field at the center. It's a super powerful tool for picturing these invisible forces. Okay, so we've covered the cause. Moving charges create magnetic fields. So for Act 2, let's talk about the effect. What do these magnetic fields actually do when another charged particle wanders into them? Well, they exert a force. We call it the magnetic force or the Lorentz force. Now, the most interesting part of this slide is right there in the formula. The force, F, depends on the charge, Q, the field B, and this is the critical part, the velocity V. The particle's speed and direction are baked right into the equation. And that leads us to the single biggest takeaway about this force. If you have a charged particle just sitting perfectly still, not moving at all, it could be in the strongest magnetic field on the planet and absolutely nothing will happen to it. Zero velocity means zero force, period. The charge has to be moving for the magnetic field to do anything. But there's another really weird thing about this force. It always pushes sideways, perpendicular to the direction the particle's already moving. Think about that for a second. If you can only push on the side of something, you can't make it speed up or slow down. All you can do is make it turn. So the magnetic force is purely a turning force. So if the only thing a magnetic field can do is make a moving charge turn, what kinds of paths do these particles actually take? Oh, this is where it gets really, really cool. So let's start with case number 1, the simplest one. A charged particle flies into a magnetic field, but it happens to be moving perfectly parallel to the field lines. Well, in this one special case, the math works out so that there's no force at all. The particle is totally oblivious to the field. It just sails right on through in a perfectly straight line. Okay, now for case 2. What if the particle flies in perfectly perpendicular to the field? Now it feels the maximum possible force. And since that force is always sideways, it's constantly yanking the particle off its straight path. The result? It gets trapped in this perfect circular dance, going round and round forever without ever changing speed. So what happens if it comes in at an angle? Not quite parallel, not quite perpendicular, but somewhere in the middle. Well, you get a beautiful combination of the first two cases. The part of its motion that's parallel to the field keeps it moving forward, totally unaffected, but the part that's perpendicular gets pulled into a circle. And when you combine moving forward with going in a circle, you get this absolutely gorgeous corkscrew path, a helix. Which brings us right back to where we started. We've seen that a wire with a current, which is just moving charges, creates a magnetic field. And we've also seen that a magnetic field pushes on other moving charges, like the ones in a second wire. So that leaves us with one last, really fascinating question to think about. What do you think happens when you put two of these current-carrying wires right next to each other? Do they attract? Do they repel? Or do they do nothing at all? The answer connects everything we've just talked about. Thanks for joining me.